Hello, chemists. So this lecture topic, atomic structure, is the last lecture series to appear on midterm one. Midterm one is scheduled to occur next week during recitation, so Thursday, September 24th, during our regularly scheduled recitation time. So this is in person. Come in during your regularly scheduled recitation time, and the midterm will be an hour long. It will be closed note. Make sure that you bring some type of writing utensil like a pen or pencil and a non-scientific calculator. You will not be permitted to use your phone or any device as a calculator. All right, so getting started with atomic structure. The past two lectures, we've talked a lot about atoms. We talked about protons and neutrons and how those subatomic particles contribute the most to atomic masses. What we haven't really talked about much are electrons. We know that electrons appear in the extranuclear region, but are there more details that we can learn about how those electrons are orbiting around the nucleus of an atom? So that brings us to atomic structure. So before we really get into the details of the structure of an atom, we need to talk about electromagnetic radiation. This is just commonly known as light. So the light that is, lighting my room right now, the light that is coming off of your screen into your eyes, that is light that we know of, but it's also considered electromagnetic radiation. Light contains energy. So we can define electromagnetic radiation, or light, as just energy particles that travel through space in the form of waves. So there's a lot of different kinds of electromagnetic waves. Like I said, it's like the white light that we see every day. Other forms of electromagnetic radiation includes X-rays, radio waves, etc. These all differ by just their amount of energy contained within these particles and within these waves. So I said that there's a lot of different types of electromagnetic radiation. They all just differ with their amount of energy that they contain. So we can kind of list all of those different types of electromagnetic radiation through the electromagnetic spectrum. So this spectrum is a continuous spectrum. There's no breaks into it, although we categorize the different types of waves with different names like radio waves, microwaves, visible light. There are no breaks. It's just continuous. These waves are arranged by energy. I said that electromagnetic radiation, we can have different kinds with different amounts of energy. And so you can see that here. We have, radio waves, microwaves, infrared waves, and then we have our visible light right here in this part of the spectrum. And then between infrared and ultraviolet, that's where our visible light region lies. And then above ultraviolet, we have X-rays and then gamma rays. And so moving from left to right, these waves and these categories that we have of waves, the energy increases. So gamma rays have the most energy contained within those waves, while radio waves are not as energetic. So we can arrange the different kinds of electromagnetic radiation by energy, like you see here. We can also arrange them by shortest to longest wavelength, and I'll get into the details about that, but essentially radio waves have the longest wavelengths, and gamma rays with the most energy have the shortest wavelengths. And then even within the visible light region, when we go from red to blue or purple, as we move from left to right here, we have long wavelengths, that's our red region, and then we have short wavelengths, that's our purple region. And as we move left to right, energy also increases. So red has the longest wavelength and the most energy, while purple has the shortest wavelength and most amount of energy within the visible region. All right, so we've been talking about energy and wavelengths, so what does all this mean? So remember when I said that light and electromagnetic radiation, it's just a wave. It's a light wave. And those waves is what defines the colors that we see in the white light in our rooms or whatever we're looking at. Because they're all light, it's all light, electromagnetic electromagnetic radiation is light, all those waves travel at the speed of light. So the speed of light is a constant. In a vacuum, it will one wave of light will travel at 3.0 times 10 to the 8 meters per second. So this is the speed of light in a vacuum. So I've been talking about white light. Where exactly does white light come from? Well, white light really originates from the sun and our various light fixtures around our house. So then where do the colors come from when only from what we see from the sun is just white light? Well, if you've ever seen a rainbow, what you're actually seeing is the continuous spectrum of colors of electromagnetic radiation within the visible region. That's essentially what a rainbow is. So if you take some type of white light, so I'll denote that, so a white light source, such as like a light bulb or the sun, and you put that white light through a prism, what will happen is that the wavelengths of colors will separate from one another and they'll spread out. So you'll take white light and it will become a rainbow. From where you see we have, red, and red light is our longest wavelength, meaning that the tops of the wave are furthest away from one another, while blue or purple, which is our shortest wavelength, these crests are closer to one another. So essentially a prism will separate that white light into the rainbow features that we're used to. So when you in nature and you're outside see a rainbow, typically what's happening is that the white light from the sun is being diffracted by water droplets in the air. So those water droplets can act like a prism and separate that white light, separating all the colors that are contained within that white light. And so this phenomena that you see of rainbows occurring from white light is a consequence of light behaving like a wave, where we can separate these different wavelengths of light, which correspond to different colors that we see. So I've kind of said this before, but each color has a corresponding wavelength and frequency. And I'll talk about frequency in the next slide. But remember, with wavelengths, that the shortest wavelengths, those are our like blues and purples, while red has our longest wavelength. So wavelength and frequency are related to one another. They're related by the speed of light. So we have this equation that relates frequency and wavelength. So remember, c is our speed of light that we know, and then nu. It's this V looking thing. It's a Greek letter, so it's actually nu. This is our frequency of light, and that has a unit of per second. So it's essentially, if I go back, or hertz, if I go back, to our wave picture, light is a wave. This wave is moving through space at the speed of light. So if I just kind of pick a point in space and just count how many crests pass this point in space as this wave is moving at the speed of light, that is our frequency. How many times one of these crests passes a certain point in space. So that's our frequency. So it's essentially per second. So this is how many crests per second pass a certain space and time when that wave is moving at the speed of light. So nu is our frequency. It's measured in per second, or hertz. And then here I have another Greek letter. This is lambda. This is our wavelength. And so this wavelength is measured in some type of distance, so in meters. Or sometimes, if we're talking about really small wavelengths, it'll be measured in nanometers or micrometers or something. All right, but with the unit of meters. So you see, if we put those units together, frequency is a per second, or a hertz. Lambda is a meter. The speed of light is a meter per second. You see how this equation, all those units balance out. When we multiply frequency and wavelength together, we get the unit of meters per second, which is velocity. So that is how wavelength, essentially the distance between these two crests, and how many crests pass a certain point in space while that wave is moving at the speed of light, That's how frequency and wavelength are related to one another. And so, essentially, if you have a really short wavelength, frequency will be very, very large in order to make up the speed of light. If you have a longer wavelength, then frequency will be less, because remember, speed of light is a constant. So maybe I can write that here. So when lambda is big, then frequency will be small. When lambda is small, when you have a short wavelength, then frequency will be big. And that's a consequence of this equation where these two factors equal a constant, which is the speed of light. Okay, so let's do a little practice problem. What is the frequency of a red laser pointer in hertz or per second if red light has a wavelength of 652 nanometers? So here is an example where we're talking about a wavelength of light that is pretty short. So we talk about it in units of nanometers. So this question is asking for frequency, which is new. All right, and that has the unit of a per second or hertz. So that's what we're after. And they're giving us a wavelength. So, I mean, the only equation that we've talked about thus far in this lecture is this one up here. So I think we're going to be using this equation up here to get our answer. But thankfully, you know, they give us wavelength. So that's this this variable. We know the speed of light, that's a constant, so we can solve for frequency. So if I rewrite that equation, so speed of light equals frequency times wavelength, I want frequency, so I'm going to just rearrange this. All right, so frequency equals speed of light over lambda. All right, I know speed of light and I know the wavelength because the question gives it to us. So perfect. So now it's just, you know, put in the numbers and plug and chug away. So C, the speed of light, is 3.00. Oops, this is not correct. This is 3.00 times 10 to the 8th. I'll fix that before I post this. So 3.00 times 10 to the 8th meters per second over wavelength, which the question gives to us, it is 652 nanometers. So remember the unit that we're after. We're after this per second or hertz unit. So if I look at the units that I have written down right now, I have a meter and I have a nanometer. So those two units won't cancel one another. I need to get them to be equal, the same unit. So before I move on with my question or with, you know, my calculation, I need to convert this nanometer to match the speed of light unit, which is a meter. So I'm going to convert nanometers to meters, so a little bit of dimensional analysis in here. So nano means 10 to the negative 9. All right, I know that there's 1 times 10 to the 9 nanometers in 1 meter. So if I now look at my units, nanometers cancel, and I'm left with meter and meter. So those two units will cancel once you put everything into your calculator. All right, I'll just do the bottom portion. I'll show you what the bottom portion of the equation looks like. So, you know, do that bottom, the denominator, math. So that's meters over 3.00 times 10 to the 8th meters per second. And you'll see that meters cancel. And then we are left with the 1 over seconds that we need to have frequency. So now if you plug that into your calculator, you should get an answer of 4.601 times 10 to the 14 per second, or 1 over seconds. So let's check our sig figs here. The number we were given, all right, both of these have 3 sig figs, so our answer needs to have 3 sig figs. So I can rewrite my true answer as 4.60 times 10 to the 14 per second or hertz. So that is our frequency of red light. So up until this point, we've talked about light as a form of a wave, that we can describe light like a wave by their wavelength and frequency, where wavelength and frequency are inversely related to one another. But I also said that light is a form of energy. So how else can we describe light to mean that it is energy. And so this is how another way that we can describe light in the form of a photon. So this is just another way to describe light. This is the same light that's coming off of your computer screen, that's coming from the sun, it's coming from your light bulbs. We can also call light photons. So a photon is just a packets of energy, of light energy. It's still light, so it's still traveling at the speed of light. So C 3.0 times 10 to the 8 meter per second. But now we're just describing it as a form of energy. And so this is the equation where we can get the energy of light. So the energy that's within a light packet or a photon is equal to Planck's constant. So H is a constant. It is 6.626 times 10 to the negative 34 joule seconds. All right, you'll never have to memorize this number. I'll always give it to you. So energy equals Planck's constant times frequency. So our frequency of light is what dictates the energy that that photon is. But remember, frequency and wavelength are related to one another, so we can also rewrite this equation using wavelength. So energy equals Planck's constant times the speed of light over lambda. Essentially, I just replaced frequency with this equation, substituting for frequency. So now we have an equation that has lambda, our wavelength. So essentially what I want you to get out of this equation is that there is a direct relationship between energy and frequency, or energy and wavelength of light. So the wave nature of light, so its wavelength or its frequency, is directly related to the energy that is contained within that photon. So high energy photons will have short wavelengths and high frequencies. Remember how short wavelengths go along with high or large frequencies? Now we added an energy component. So now low energy photons will have long wavelengths or low frequencies. So let's take a look at the electromagnetic spectrum again. A different picture. This one's interesting looking. So remember our electromagnetic spectrum. This is the same spectrum as the previous slides. It's continuous. There are no breaks. But remember how I told you that it's arranged by energy and by wavelength and by frequency, because all of these terms are related to one another by those equations that I showed you. So if we look here, we have radio waves. So these are our low energy, long wavelengths, and low frequencies. And then on the high energy side of the electromagnetic spectrum, we have gamma rays. So gamma rays will contain a lot of energy, high energy. These high energy photons can pierce through skin and destroy cellular tissue. So high energy photons, it is a short wavelength, and it is a high frequency. So that's just putting all of those concepts together that we just looked at. So a lot of what we'll be focusing in on is the visible region. And so where the visible region lies within the electromagnetic spectrum, the red side of the rainbow of our visible region is more towards the long wavelength, low frequency, low energy portion, while purple and blue are towards our high energy, short wavelength, high frequency side of the electromagnetic spectrum. So you see on the visible side, right to the right of the visible side, we have ultraviolet. And so ultraviolet light also comes from the sun. And so this is why you get sunburned on really bright days. But that ultraviolet light has a little bit more energy than visible light, and that's enough energy to break bonds in our skin and cause burning. And so you might know this as UV light or ultraviolet light. So UV is just short for ultraviolet. Okay, so why is light related to atomic structure? You might have forgotten that we're learning about atomic structure. How does this have to do with atoms? Well, it has to do with atoms because every atom has a unique atomic spectrum that comes from it. So an atomic spectrum is a discontinuous spectrum of light that is emitted by an atom when it is excited. And what I mean by excited is like when we put energy into it, either in the form of like an electrical current or light itself. We can excite an atom for it to emit its atomic spectrum. So you've seen atomic spectra before. A neon sign, what you're seeing in a neon sign, those tubes are filled with neon. Electricity runs through the sign and it excites neon atoms. And the light you see is actually the atomic spectrum of neon. So that neon signs are an example of real life atomic spectra. So, all right, atomic spectrum. So essentially, I say it's discontinuous because before when we talked about rainbows and white light being separated by a prism into the rainbow colors, that is a continuous spectrum. While an atomic spectrum, you see discrete lines of different colors when light from your atomic spectrum passes through a prism. All right. The photons that you see from an atomic spectrum, like in a neon sign, the light that you see from the neon atomic spectrum, are a consequence of electrons moving between energy levels. So finally, we're talking about electrons and the details about electrons. So this is why, since electrons moving within an atom or between energy levels produce photons, this is why we had to talk about the electromagnetic spectrum first, before we could get into the details about electrons and then finally atomic structure. So with electrons, when they move between energy levels, they can either absorb a photon. An atom can absorb a photon. So photons are absorbed into the atom, or electrons, when they move between energy levels, a photon can be emitted. So essentially light coming from the atom into space, and into our eyes. So the details about the movement of electrons between energy levels, just to kind of summarize it, is energy will be, or a photon energy will be absorbed when an electron moves to a higher energy level than it was initially. Or a photon will be emitted when an electron moves to a lower energy level. So the neon signs that you see, you are seeing emitted photons. So in a neon atom, electrons will be moving to lower energy levels. So light will be emitted, and that's why neon signs work the way they do. Let's get into a little bit more detail about electron energy levels. Remember, photons or energies are absorbed when electrons move to higher energy levels. Energy or photons are emitted, like in our neon sign, when electrons move to lower energy levels. Essentially, energy levels are like a ladder. You can think of them as like a ladder, these specific orbits around the nucleus of an atom where the electrons reside. These energy levels are specific, like rungs of a ladder, where the lowest rung, or the most stable n equals 1 energy level, is at the bottom of our ladder and it's closest to the nucleus. So you can go up one more rung to our energy level of n equals 2, where an electron can reside at a higher energy level, or n equals 3, n equals 4, n equals 5. So these are essentially specific rungs of a ladder or specific orbits around our atom's nucleus. So these are the specific energy levels that I've been talking about. You count them in integer numbers, 1, 2, 3, 4, 5, 6, so on. And so the energy increases as you go up the rungs of the ladder, or as you increase your energy level, that you're increasing your energy of those specific energy levels. And again, electrons with the lowest energy are closest to the nucleus. So that means our bottom rung, n equals 1, is closest to the nucleus. And remember, you see that energy levels can only be these integer values. So you cannot have electrons between an energy level. They can only exist on these specific rungs. So think about this ladder analogy when thinking about electron energy levels. If an electron goes from n equals 5 all the way down to n equals 1, you are moving to a lower energy level. So that means energy or a photon must be emitted if an electron goes from 5 to 1. Or you can think if an electron goes up the ladder, that you must put energy or photon energy into the atom in order for that electron to jump from a lower rung to a higher rung. So this kind of just summarizes that that ladder analogy. For an electron to absorb a photon, it must jump up to a higher energy level. So that's what these lines are. They're just representing different energy levels. So if an electron moves to a higher one, energy must be absorbed. But then if that electron falls to a lower energy level, then a photon is emitted. You can send differing amounts of energy into an atom. So if I were to send a really large amount of energy or a large energy photon into an atom, that electron would be excited to an even higher energy level, higher than the example that I had up here before. And then if an electron falls a greater distance, falls from a higher rung of our ladder to a lower rung, then an even higher energy photon will be emitted. So it all kind of goes back to this ladder analogy. If you fall from a higher place, a higher energy photon will be emitted versus when compared to falling from a lower rung to n equals 1, then a lower energy photon will be emitted. All right, so what does this have to do with our elements and our specific atoms that are on the periodic table? Well, I said before that every atom has a specific signature of their atomic spectra. So this is an example of the atomic spectrum for hydrogen gas. So you can see that here. So if we took a tube filled with hydrogen gas and excited it, we would see light emitting. It would look like this, although when our eyes see it, it's actually a combination of all those colors. So what you're seeing here is we send the light from a hydrogen discharge tube through a prism, and we separate the different colors of light. So essentially, a hydrogen discharge tube will have these 4 specific lines, and this is signature to the hydrogen atom. So each of these lines corresponds to a different transition between energy levels. So you can see here our red line, red being our lower energy photons, our lowest energy photon. This red line comes from an electron falling from the n equals 3 to n equals 2 energy levels. So the energy difference between n equals 3 and n equals 2 is equal to an energy difference that relates to this wavelength, 656 nanometers. And this would be red light corresponding to our electromagnetic spectrum in the visible region. So if we move over to slightly higher energy, we see that there's this 486 nanometer line. This line comes from an electron falling from n equals 4 to n equals 2 energy level. So you see that this electron is falling further than our red example. So this energy difference is larger. So the photon that's emitted from this transition, from this electron falling from n equals 4 to n equals 2, is a larger energy than n equals 3 to n equals 2. So this line, this color that is emitted has higher energy than our red line. And then you keep going. These 2 purple lines are from electrons falling from n equals 5 to n equals 2. And then the highest energy line, 410 nanometers, comes from an electron falling from n equals 6 to n equals 2. So all of these examples that I've shown you are examples of electrons falling from higher energy levels to lower energy levels where a photon is emitted. right? So this, what you see right here, is the emission spectrum of a hydrogen discharge tube. We call this spectrum with discrete lines an emission spectrum because this is the spectrum that results from emitted photons from the electrons falling of the hydrogen discharge tube. So you're seeing emitted photons. So this contrasts to our next slide. So we have our hydrogen emission spectrum down here. It's the same one from, or a similar one than the one in the previous slide. And then so what you see up here is the hydrogen absorption spectrum. So you can kind of see that there's a black line at every point that there was a line in our emission spectrum. So what this graph, or what this spectrum is showing you, are that at these lines, at these certain wavelengths, are where a hydrogen sample will absorb photons. So if we send white light through a hydrogen sample, what our eyes would see are all of the wavelengths that were not absorbed by the sample. So that's what you're seeing here. Our eyes would see this absorption spectrum. Because at these certain wavelengths, right here, all of these correspond to certain energy level transitions, right? This was our n equals 3 to n equals 2. So now we're essentially in the absorption spectrum, we're sending an electron going up the ladder. So in the emission spectrum, we're going from n equals 3 to n equals 2, but in the absorption spectrum, we are going from n equals 2 to n equals 3. All right, and then this like really light blue line would be the transition between n equals 2 to n equals 4. So essentially we're going up the ladder and then rising to higher energy levels, while at this bottom emission spectrum, we fall down the ladder. Right, so this is how these two spectra are related to one another, right? Where the emission spectrum, we're falling, going to lower energy levels, while in the absorption spectrum, we are doing the opposite. We are going from the lower energy level to the higher energy level. And then so these lines, the higher energy lines, would just correspond to going from n equals 2 to n equals 5, or n equals 2 to n equals 6. And when we go up to higher energy levels, that atom is absorbing energy, or absorbing photon energy. And that's why you see these black lines in those places, because the sample is absorbing those specific wavelengths. And then our eyes would see all of the other colors of the rainbow that were not absorbed. Keep in mind that hydrogen is not the only element that has a absorption or emission spectrum. Every element has a unique atomic spectra that can actually help us identify a lot of the different elements. So, we have our hydrogen atomic spectrum that you've seen, that's up top. Next, the next element, helium. The helium atomic spectrum actually looks very distinct from the hydrogen atomic spectrum. See that we have this yellow line that appears in the helium spectrum. And remember, all of these lines corresponds to different transitions between between energy levels, different energy levels. And because these are all emission lines, it means electrons are falling from higher energy levels to lower energy levels. Helium is interesting because helium is the only element that was not discovered on Earth first. Helium is in our sun. The sun undergoes nuclear fusion. It combines two hydrogen atoms and smashes them together to make a helium atom. And so what scientists did is they first saw helium through its atomic spectrum in the sun. Essentially, they took some of the light from the sun and they split it into its atomic, using a prism. They split it and they saw these lines appear, and they saw this new yellow line, and they knew that this yellow line did not cannot occur from the hydrogen atom, because there's no yellow line in the atomic spectrum of hydrogen. So they knew that there was this new element in the sun because of this new yellow line. And that's a consequence of all the atomic spectrum and spectra from all of the different elements have a unique signature. So they first saw helium actually in the sun before they discovered it on Earth. And then some of the other elements have other atomic spectra. Neon looks like this, sodium has these lines, and mercury has these lines, where all of these lines are from transitions between different energy levels. And because these are emitted electrons, these electrons are falling from higher energy levels to lower energy levels. So let's make sure we're understanding energy levels and absorption versus emission with a learning check. So let's read through these prompts and indicate if the energy or photon is absorbed, is it emitted, or is there no change? So I'll mention there's no change when there's no change in energy level. And let's just remind ourselves, energy is absorbed, or a photon is absorbed when the energy level increases or goes up in number, and then we have an emitted photon when the energy level decreases, or when a electron falls from a higher energy level to a lower energy level. All right, so the first one. An electron moves from the first energy level, n equals 1, to the third energy level, n equals 3. So we're going from n equals 1 to n equals 3. So since we're increasing our energy level from 1 to 3, this would be absorption. That energy or light is absorbed. Okay, and then the second one. An electron falls from the third energy level to the second energy level. So we're going from n equals 3 to n equals 2. So since we're falling to a lower energy level, that electron's falling to a lower energy level, this would result in an emitted photon. And then finally, an electron moves within the third energy level. So if it's only moving within the third, it's going essentially from n equals 3 to n equals 3. So there's no change in energy level. So this would have no change in energy. Essentially, there's no energy being absorbed. There's no energy being emitted.